Welcome all nerds, geeks, students, friends, and family to this exploration of game mechanics from ancient games to AI-driven futures. Whether you're preparing for a game jam, studying game design, or simply curious about how games work, this presentation will give you both historical context and practical knowledge. We'll journey through thousands of years of game design, explore cutting-edge AI applications, and discover timeless principles that will help you create compelling games. Let's begin. Now ask yourself, what games do you actually play? Are you primarily a mobile gamer, console player, or PC enthusiast? Do you gravitate toward competitive games or casual experiences? Do you prefer single-player narratives or multiplayer social experiences? And what's your current favorite game? Understanding your own gaming preferences helps you recognize your design biases and broadens your perspective. The games you play influence the games you'll create, so it's worth reflecting on your habits and preferences. Games are not a modern invention. They're fundamental to human civilization. In ancient Egypt, over 3,500 years ago, people played Senet, a board game found in royal tombs including Tutankhamun's. The royal game of from Mesopotamia dates back 4,600 years. Mehen, the snake game, might be even older. These weren't just entertainment. They served religious, educational, and social functions. They taught strategy, reinforced cultural values, and connected communities. From the very beginning, games have been sophisticated systems with rules, goals, challenges, and meaningful consequences. The fundamental elements of game design were established millennia ago. In 1770, Wolfgang von Kempelen unveiled the Mechanical Turk, a chess-playing automaton that toured Europe defeating human opponents, including Napoleon Bonaparte and Benjamin Franklin. It appeared to be a thinking machine, a marvel of mechanical engineering. In reality, a human chess master was hidden inside the cabinet, manipulating the pieces through an ingenious system of magnets and levers. This raises profound questions that remain relevant today. What constitutes intelligence? When does simulation become indistinguishable from reality? Is the illusion of intelligence sufficient if it produces the desired experience? In game design, we constantly create these illusions. Our NPCs don't actually think, but if they create the experience of intelligent opposition, they've succeeded. The Mechanical Turk reminds us that perceived intelligence can be as valuable as actual intelligence. Ancient Rome transformed games into spectacular public entertainment that served political and social functions. Gladiatorial combat beginning in 264 BC wasn't just violence. These were carefully choreographed spectacles with rules, referees, and audience participation. Gladiators were celebrities. Animal contests like cockfighting were equally popular, with complex betting systems and breeding programs. Today, cockfighting is banned in most countries. One exemption, however, is Bali. The Roman poet Juvenal coined the phrase bread and circuses to describe how the government maintained social order. In German, we said Brot und Spiele, provide food and entertainment and the population remains content. Games were political tools as much as entertainment. This teaches us that games have always served purposes beyond play. They teach, socialize, reinforce cultural values, and provide safe spaces for competition and risk-taking. Every human civilization developed unique games reflecting their values and social structures. Mancala, played across Africa and the Middle East for thousands of years, teaches mathematical thinking and resource management through simple count-and-capture mechanics. Go, originating in China over 2,500 years ago, reflects philosophical concepts of balance, influence, and the value of empty space. Chess evolved from the Indian game Chaturanga, spreading through Persia to Europe, reflecting medieval social hierarchies through its different pieces. Playing cards, invented in Tang Dynasty China, spread along trade routes and adapted to local cultures. Games are cultural mirrors. They reflect the values, social structures, and philosophical concepts of their originating cultures. When you design games, you're not just creating entertainment. You're creating cultural artifacts that will reflect and potentially shape values. The stereotype of the gamer as a young male in a basement is completely outdated. Gaming has become humanity's most widespread interactive entertainment with 3.4 billion players globally. That's nearly half of all humans on Earth. The gender split is almost equal, 53% male, 47% female. The average age is 41 years old, not teenagers. 80% of players are adults. 60% of US adults play weekly. Asia Pacific leads with 1.48 billion players. This means your audience is everyone. When you design games, you're not designing for a narrow demographic. You're designing for humanity. This diversity means different players have different motivations, different skill levels, different cultural backgrounds, and different needs. One size doesn't fit all. Gaming engagement remains high across all age groups, but preferences shift dramatically with age. 80% of 16 to 24-year-olds play online games, favoring competitive multiplayer, action games, and social gaming. 25 to 34-year-olds represent peak gaming years with diverse preferences and willingness to invest time in complex games. 35 to 54-year-olds prefer strategy, simulation, and story-driven games. 55 to 64-year-olds gravitate toward puzzle games, casual games, and social games. Even among those 65 and older, 48% play online games, finding cognitive benefits, social connection, and entertainment. Younger players favor action, competition, and fast-paced experiences. Older players prefer strategy, narrative, and cognitive challenge. When you design, consider your target age group's preferences, but also remember that accessibility features and thoughtful difficulty curves benefit players of all ages. Ask yourself, why do you actually play games? Do you play to relax or to challenge yourself? Do you seek social connection or do you play to escape? Are you driven by competition or by the desire to create? And most importantly, what keeps you coming back to your favorite games? Understanding your own motivations helps you design for others. We all play for different reasons, and the most engaging games satisfy multiple motivations simultaneously. Take a moment to reflect on what truly drives your gaming behavior. Self-determination theory, developed by psychologists Deci and Ryan, explains human motivation through three fundamental psychological needs. First, autonomy, the need to feel in control of your own actions and decisions. In games, this manifests as meaningful choices that affect outcomes, multiple paths to goals, player agency in shaping the experience, and freedom to experiment and explore. Second, competence, the need to feel effective and capable. In games, this means clear feedback on performance, achievable challenges that stretch abilities, progression systems that show growth, and mastery opportunities. Third, relatedness, the need to feel connected to others. In games, this includes social interaction and cooperation, shared experiences, competition and comparison, and community belonging. Ryan, Rigby, and Przybilski applied this theory specifically to gaming in their influential 2006 paper, which has been cited over 5,000 times. They found that games satisfying all three needs create the most engaging experiences. When you design, ask yourself, does my game provide meaningful choices? Does it offer clear feedback and achievable challenges? Does it create opportunities for social connection? The most successful games fulfill all three needs simultaneously. Several models help us understand different player motivations. Richard Bartle's 1996 player types identified four categories. Achievers want to complete goals, collect achievements, and master systems. They're driven by competence. Explorers want to discover content, understand systems, and find secrets. They seek autonomy and competence. Socializers want to interact with others, build relationships, and share experiences. They're motivated by relatedness. Killers want to compete, dominate, and impact others. They seek both competence and relatedness. Alexander Pfeiffer added the player type of the time player in 2018, saying that all of the four core player types might play games to fight time and boredom. Playing games for only a couple of minutes, for example, while riding the bus. This is possible because modern smartphone games. Nick Yee's 2006 motivational components identified three dimensions: achievement, including advancement, mechanics, and competition; social, including socializing, relationships, and teamwork; and immersion, including discovery, role-playing, customization, and escapism. Quantic Foundry's data-driven approach, based on analyzing over 300,000 gamers, identified six primary motivations: action, social, mastery, achievement, immersion, and creativity. All these models ultimately map back to autonomy, competence, and relatedness. Different mechanics appeal to different player types. You can't satisfy everyone in a limited development time. Choose your target player type and design mechanics that satisfy their primary motivations. A focused experience for one player type beats a diluted experience trying to please everyone. Early video game AI was remarkably simple, yet it created compelling experiences through clever design. Space Invaders from 1978 featured aliens following simple movement patterns: move right, drop down, move left, repeat. As you destroyed aliens, the remaining ones moved faster. This wasn't intentional difficulty design. It was a technical limitation. The processor had fewer sprites to update, so they moved faster. But this accidental feature became a brilliant game mechanic, creating tension and urgency. Duck Hunt, from 1984, featured ducks following pre-programmed flight paths with random variations. There was no actual intelligence, just randomized patterns. But it worked. Pac-Man, from 1980, gave each ghost a unique algorithm. Blinky chases Pac-Man directly. Pinky tries to position ahead of Pac-Man. Inky uses complex positioning relative to Blinky and Pac-Man. Clyde chases until close, then retreats. These simple rules create emergent complexity and strategic depth. The lesson? Game AI prioritizes fun over intelligence. It should be predictable enough that players can learn and develop strategies, random enough to remain challenging and surprising, fair so players feel victories are earned, and performant so it doesn't slow down the game. Don't overcomplicate AI. Simple, well-tuned behaviors often create better gameplay than complex systems. For decades, chess was considered the ultimate test of machine intelligence. The journey from the Mechanical Turk's deception to Deep Blue's victory tells us much about both AI and game design. In 1950, Claude Shannon published Programming a Computer for Playing Chess. The first chess program was created at Los Alamos in 1956. Throughout the 70s and 80s, chess computers gradually improved. Then in 1997, Deep Blue defeated world champion Garry Kasparov. Deep Blue's approach was brute force calculation, evaluating 200 million positions per second using specialized hardware custom designed for chess. It used an opening book database of known sequences, endgame tables for perfect play in simplified positions, and evaluation functions with heuristics to assess position quality. What Deep Blue proved was that machines could surpass humans in complex strategic tasks, that narrow intelligence could exceed general intelligence, and that computational power could compensate for lack of understanding. What Deep Blue didn't prove was that it understood chess. It calculated but didn't comprehend. Success required specialized hardware and programming that doesn't generalize to other problems. There was no creativity or intuition, just calculation. For game design, this teaches us that brute force has limits. Deep Blue's approach works for chess's finite possibility space, but not for open-ended games. Specialization versus generalization matters. Narrow AI can excel at specific tasks. Human experience still matters. Kasparov's intuition and creativity made him competitive despite computational disadvantage. And players don't care if AI thinks, they care if it creates engaging challenges. Go was considered impossible for AI to master using traditional approaches. The game's vast possibility space, with 10 to the power of 170 possible board positions, made brute force calculation infeasible. That's more than the number of atoms in the observable universe. When AlphaGo defeated Lee Sedol in 2016, one of the world's top Go players, it marked a fundamental shift in AI capabilities. This wasn't just a faster calculator. It was a system that developed intuition. AlphaGo used deep neural networks that learned pattern recognition from millions of games, Monte Carlo tree search that evaluated promising moves rather than all moves, a policy network that predicted which moves experts would make, a value network that evaluated board positions, and reinforcement learning that improved through self-play. In Game 2 against Lee Sedol, AlphaGo made move 37, which human experts initially thought was a mistake. It was actually brilliant, demonstrating creativity beyond human play patterns. This showed that AI hadn't just learned human strategies. It had developed novel approaches. AlphaGo Zero, released in 2017, learned entirely from self-play without human game data. It surpassed the original AlphaGo in just 3 days and discovered novel opening sequences and strategies. For game design, this teaches us that machine learning enables emergent behavior. AI can develop strategies designers didn't program. Intuition can be learned through pattern recognition via neural networks. Self-play creates innovation as AI playing against itself discovers novel strategies. And creativity isn't uniquely human. Machines can generate genuinely creative solutions. While you won't implement AlphaGo in a game jam, the principles apply. Simple rules can create deep strategic complexity. Emergent behavior is more interesting than scripted responses. Testing reveals unexpected strategies, and sometimes mistakes lead to innovation. Modern esports games present challenges far beyond board games. Real-time decision-making, imperfect information, teamwork, and continuous action. OpenAI 5 in 2018 defeated professional Dota 2 teams. It managed 5 AI agents cooperating in real time, handled 20,000 possible actions per agent, and learned through 180 years of gameplay per day in simulated time. It demonstrated coordination, strategy, and adaptation. AlphaStar in 2019 reached Grandmaster level in StarCraft II, placing in the top 0.2% of players. It managed real-time strategy with resource management, unit control, and long-term planning, and operated under human-like constraints with limited actions per minute. It showed strategic diversity across different playstyles. Beyond playing, AI now analyzes esports matches to predict outcomes based on team compositions and player performance, provide coaching by identifying mistakes and suggesting improvements, generate highlights by automatically detecting exciting moments, and track performance metrics measuring player skills across multiple dimensions. For game design, this teaches us that complexity is manageable. AI can handle games too complex for traditional programming. Emergent teamwork happens as multiple AI agents coordinate without explicit programming. Human-like constraints matter because AI that plays fairly creates better experiences, and analytics enhance experience, as understanding gameplay through data improves both playing and watching. Pathfinding is one of the most common AI challenges in games. How do NPCs navigate complex environments intelligently? The A-star algorithm has been the industry standard since the 1960s. It finds the optimal path from start to goal, balancing between shortest path and computational efficiency, using heuristics to guide search toward the goal. It works by evaluating possible moves, estimating distance to goal, choosing the most promising path, and repeating until the goal is reached. Navigation meshes divide the game world into walkable regions, define connections between regions, enable efficient pathfinding in three-dimensional spaces, and support dynamic obstacles. Dynamic obstacle avoidance handles moving obstacles like other NPCs, players, and vehicles. It adjusts paths in real time, creates natural-looking movement, and prevents NPCs from getting stuck. Crowd simulation manages multiple agents simultaneously, prevents collisions and clustering, creates natural flow of crowds, and balances individual goals with group behavior. Why does this matter? Smooth, believable movement is essential for immersion. When NPCs navigate intelligently, players accept them as inhabiting the game world. When pathfinding fails, with NPCs walking into walls, getting stuck, or taking nonsensical routes, immersion breaks. Most game engines provide pathfinding tools. Use them. Don't implement A-star from scratch unless pathfinding is your core mechanic. Focus on clear walkable areas, reasonable obstacle placement, testing NPC movement early, and simple behaviors that look intelligent. Video games have become essential tools for AI research, providing controlled environments for testing and training AI systems. Why use games for AI research? They offer controlled environments with consistent rules and reproducible scenarios. They provide scalable difficulty from simple to extremely complex. They enable safe testing with no real-world consequences for failures. They give rich feedback with clear success and failure signals. They offer computational efficiency as simulation runs faster than real-time. And they present diverse challenges as different games test different capabilities. Major research platforms include the Atari Learning Environment, with 57 classic Atari games providing a standardized testing environment. DeepMind's DQN learned to play from pixels alone, demonstrating general learning algorithms. DeepMind Lab offers three-dimensional navigation and puzzle solving from a first-person perspective, testing spatial reasoning, memory, and planning. Minecraft provides open-ended creativity and problem-solving in infinite procedurally generated worlds, testing long-term planning, resource management, and exploration. Microsoft's Project Malma uses Minecraft for AI research. Transfer learning means skills learned in games can transfer to real-world applications. Navigation algorithms transfer to autonomous vehicles. Object recognition transfers to computer vision systems. Strategy development transfers to resource allocation. And multi-agent coordination transfers to robotics. If your game is complex enough to challenge AI, it's probably complex enough to engage human players. The inverse is also true. If AI solves your game too easily, players might find it shallow. Now ask yourself, have you actually noticed AI in the games you play? Think about the enemies you've faced. Were they smart or predictable? Have you encountered NPCs that felt truly alive, that surprised you with their behavior? Have you played games that seemed to adapt to your skill level or play style? Can you remember specific moments when AI surprised you either positively or negatively? Becoming aware of AI in games helps you design better AI yourself. Once you start noticing these systems, you'll see them everywhere, and you'll develop intuition for what works and what doesn't. When AI systems optimize for stated goals, They sometimes discover exploits that technically achieve the objective while violating the spirit of the game. These failures teach important lessons about game design. OpenAI's Coast Runners in 2018 was intended to win a boat race. The reward system gave points for hitting targets. The AI discovered it could get more points by going in circles hitting the same targets repeatedly rather than completing the race. The lesson? AI optimizes exactly what you measure, not what you intend. Hide-and-seek agents in 2019 were supposed to have one team hide while the other team seeks. Unexpected behaviors emerged. Hiders learned to move boxes to create barriers. Seekers learned to use ramps to jump over barriers. Hiders learned to lock ramps away before seekers could use them. Then seekers discovered physics glitches to surf on boxes through barriers. The lesson? Emergent strategies can exploit unintended mechanics. AI discovering exploits reveals design flaws, unclear objectives, misaligned incentives, exploitable mechanics, and unintended interactions between systems. Why does this matter for game design? First, players will find exploits. If AI can discover them through trial and error, players will find them too. Second, test your reward systems. Ensure what you're measuring aligns with what you want. Third, embrace or fix emergent strategies. Decide if exploits are features or bugs. Fourth, clear objectives matter. Ambiguous goals lead to unexpected optimization. Famous game exploits that became features include rocket jumping in Quake, combos in Street Fighter II, and bunny hopping in Counter-Strike. Sometimes the bugs are the best features. Contemporary game AI has shifted from scripted behaviors to dynamic, adaptive systems that enhance player experience. Dynamic difficulty adjustment monitors player performance in real time, adjusts challenge to maintain flow state, and makes subtle changes players don't consciously notice. Examples include Resident Evil 4's adaptive enemy spawning and Left 4 Dead's Director AI. Procedural content generation creates unique content for each playthrough, including levels, quests, and items. It balances randomness with design constraints. Examples include Minecraft worlds, No Man's Sky planets, and Spelunky levels. Behavior trees provide modular, hierarchical AI decision-making that's more flexible than finite state machines and easier to design and debug. They're the industry standard for complex NPC behavior. Director AI, like in Left 4 Dead, manages pacing and intensity, spawns enemies based on player stress levels, creates dramatic moments, and ensures varied experiences across playthroughs. Utility AI has NPCs evaluate multiple possible actions and choose based on current context and needs. This creates more believable, less predictable behavior. Examples include The Sims character decisions and fear. Enemy tactics. The key shift in philosophy is that modern game AI focuses on enhancing player experience rather than defeating players. The goal is to maintain appropriate challenge, create believable worlds, generate variety and replayability, and adapt to individual player styles. When you create games, start simple. Basic AI that works beats complex AI that doesn't. Focus on feel. Does the AI create the experience you want? Use engine tools. Most engines provide behavior trees, pathfinding, and other AI systems. Test with real players. What feels challenging to you might not to others. And iterate on tuning. Small parameter changes dramatically affect feel. Large language models like GPT-4 are beginning to transform NPC interactions, enabling truly conversational characters. Traditional NPC dialogue uses pre-written dialogue trees with limited player responses and predictable conversations. It breaks immersion when options don't match player intent. LLM-powered NPCs can respond naturally to any player input, remember previous conversations, maintain consistent personalities, generate contextually appropriate responses, and enable emergent storytelling. Current examples include AI Dungeon, a text-based adventure with GPT-powered narration where players can attempt anything they can describe, and the AI generates consequences and continues the story. This demonstrates potential but also challenges. Experimental RPG implementations have modders adding ChatGPT to Skyrim NPCs, research projects exploring conversational quest-giving, and indie games experimenting with AI-driven narratives. Challenges include lore consistency, as LLMs might contradict established game facts. Inappropriate responses can occur without careful prompting. Computational cost is significant, as running LLMs requires substantial processing power. Latency matters because response time needs to feel natural. Player expectations change once players know NPCs are AI as they test boundaries. And narrative control becomes difficult when maintaining story structure with open-ended conversations. Potential solutions include constrained generation to limit LLM responses to fit game context, hybrid approaches using LLMs for natural language understanding, but scripted responses for key moments, character cards that define NPC personality, knowledge, and goals, moderation layers to filter inappropriate content, and local models using smaller, specialized models that run efficiently. LLMs enable new game genres, conversation-focused detective games, social simulation with meaningful dialogue, educational games with natural tutoring, and therapy and mental health applications. For practical implementation, integrating LLMs in a game jam is challenging but possible. Use APIs like OpenAI or Anthropic rather than running models locally. Focus on a narrow use case, perhaps one conversational NPC. Have fallback responses for API failures. Budget for API costs. And test extensively for inappropriate responses. Ask yourself, where have you encountered gamification in your daily life? Think about learning apps. Have you used Duolingo with its streaks and levels, or Khan Academy with its badges and progress tracking? What about fitness trackers? Do you use Fitbit challenges or Apple Watch activity rings? Consider social media. Aren't likes, followers, streaks, and engagement metrics all forms of gamification? And what about loyalty programs? Starbucks rewards, airline miles, credit card points. Gamification is everywhere. Recognizing these patterns helps you understand how game mechanics can motivate behavior beyond entertainment. But it also raises ethical questions about manipulation versus enhancement. Gamification takes the motivational power of games and applies it to contexts beyond entertainment. Core elements include points for quantifiable progress measurement, badges for visual achievements and recognition, leaderboards for social comparison and competition, levels and tiers for progression systems, challenges for goal-oriented tasks, and rewards as incentives for completion. Gamification taps into intrinsic human desires for achievement through completing goals and earning rewards, recognition through badges, levels, and public acknowledgement, mastery through improving skills and progressing, social connection through leaderboards and team challenges, and autonomy through choosing which challenges to pursue. Applications span education with Khan Academy badges, Duolingo streaks, and classroom leaderboards. Business training uses corporate learning platforms and onboarding games. Healthcare includes fitness tracking, medication adherence, and rehabilitation exercises. Marketing employs loyalty programs and engagement campaigns. And employee engagement uses performance tracking and team competitions. However, there's a critical warning. Over-reliance on extrinsic rewards can undermine intrinsic motivation. This is called the over-justification effect. If people do something because they enjoy it, that's intrinsic motivation. If you add external rewards, that's extrinsic motivation. They may start doing it only for the rewards. Remove the rewards and they stop the behavior. For example, children who enjoy reading might read less if you pay them per book, because reading becomes work rather than pleasure. Effective gamification supports existing motivation, enhancing rather than replacing intrinsic interest. It provides meaningful feedback through progress indicators that inform, not just reward. It enables autonomy as players choose their path. It creates social connection through shared experiences, not just competition. And it avoids chocolate-covered broccoli, meaning it must be genuinely engaging, not just rewards on boring tasks. Understanding gamification helps you design mechanics that motivate players. Ask yourself, why would players want to engage with your mechanics? Are you providing meaningful feedback? Does progression feel rewarding? Are you creating intrinsic or extrinsic motivation? Alexander Pfeiffer, Stephen Bazina, and Thomas Wernbacher came up with a new definition of gamification in 2024. They say that gamification is the use of game mechanics as a further dimension within and around both gaming and non-gaming contexts, in an endeavor to nudge participants to perform certain actions by adopting a playful attitude. Fundamentally, gamification relies on data analysis to transform complex participant interactions into clear, engaging outcomes. This approach leverages data-driven insights to create immediate, understandable rewards, with the final goal of enhancing participant engagement and driving sustained action. Serious games are designed with a primary purpose other than pure entertainment, whether that's education, training, health, policy, or social change. Defining characteristics include a primary goal of learning, training, or behavior change, a secondary goal of entertainment to maintain engagement, measurable outcomes to assess effectiveness, and real-world application where skills transfer beyond the game. Application domains include education with K-12 curriculum games, higher education simulations, professional training, and skill development. Healthcare uses medical training through surgical simulators, patient education for disease management, rehabilitation with physical therapy games, and mental health through therapeutic interventions. Military applications include tactical training, strategic decision-making, equipment operation, and team coordination. Corporate uses include employee onboarding, skills development, compliance training, and leadership development. Policy and social change applications include public awareness campaigns, behavior change initiatives, civic engagement, and environmental education. Why do serious games work? They provide engagement through intrinsically motivating experiences. They offer safe failure where you learn from mistakes without real-world consequences. They enable active learning through doing rather than passive consumption. They give immediate feedback for rapid iteration and improvement. They improve retention as interactive experiences create stronger memories. They offer scalability through digital distribution reaching wide audiences. And they provide measurability to track learning outcomes and effectiveness. Flight Simulator from 1982 pioneered serious games by training pilots in safe environments. Modern flight simulators are so realistic that pilots can log training hours toward certifications. Multiple meta-analyses show serious games improve knowledge retention compared to lectures, skill transfer to real-world contexts, engagement compared to traditional training, and cost-effectiveness compared to in-person training. Design challenges include balancing fun and learning, as too much fun distracts from learning while too little fun loses engagement. Transfer of learning requires ensuring skills learned in-game apply to real contexts. Assessment means measuring learning outcomes effectively, and stakeholder buy-in involves convincing institutions to adopt games. When you consider designing a serious game, choose a specific learning objective, design mechanics that teach through play, provide clear feedback on performance, and make the learning goal intrinsic to gameplay. G. and Wagner said game goal has to equal the learning goal. Alexander Pfeiffer states it a bit different. He says the game world as the expected learning outcome. Nudging, developed by behavioral economists Richard Thaler and Cass Sunstein, with Thaler winning the Nobel Prize in 2017, uses choice architecture to guide people toward better decisions without restricting freedom. The core principle is libertarian paternalism. Libertarian means preserving freedom of choice. Paternalism means guiding toward beneficial outcomes. The method is designing how choices are presented. Key nudging principles include default options, as most people accept defaults, so strategic defaults guide behavior. Examples in games include autosave-enabled, recommended difficulty, and default control schemes. Feedback loops provide immediate, clear feedback that reinforces desired behaviors through visual and audio cues shaping player actions. Examples include health bars, damage numbers, and progress indicators. Framing effects show that how choices are presented influences decisions. Gain 100 health versus avoid losing 100 health trigger different responses. Examples include highlighting recommended options and positive versus negative framing. Social proof shows what others do to influence behavior. Most players chose this or leaderboards nudge conformity. Examples include 95% of players help the NPC or popularity indicators. Commitment devices show that small commitments lead to larger ones. Examples include tutorials that gradually increase commitment and daily login rewards. Salience makes certain options more noticeable. Examples include highlighting recommended paths and visual emphasis on important choices. Every game design decision is choice architecture. Tutorial design determines what you teach first. UI layout determines what's easy to access. Difficulty curves determine when you challenge players. Reward timing determines when you provide feedback. And default settings determine what's enabled by default. Nudging can enhance experience or exploit vulnerabilities. Positive nudging helps players learn mechanics, guides towards satisfying experiences, reduces frustration, and improves accessibility. Exploitative nudging manipulates spending through dark patterns, creates addictive behaviors, exploits psychological vulnerabilities, and prioritizes profit over player welfare. You're already nudging players through design choices. Which mechanics do you introduce first? What feedback do you provide? How do you guide players toward your intended experience? And are your nudges helping or manipulating? Game-based assessment transforms evaluation from stressful tests into engaging experiences, measuring learning unobtrusively while players focus on gameplay. Traditional assessment has problems. Test anxiety causes stress that impairs performance. Snapshot evaluation provides only a single high-stakes moment. Artificial context disconnects from real-world application. And limited scope measures what students know, not how they think. Game-based assessment offers advantages. It reduces test anxiety as players engage with assessment as gameplay, not examination. Stress-free environments reveal true capabilities. Multiple attempts without penalty are possible. An example is Physics Playground, which measures understanding through puzzle solving. It provides continuous formative assessment with ongoing feedback throughout gameplay, identifies learning gaps in real time, and enables immediate intervention. An example is Dragonbox, which teaches algebra through gameplay without players realizing they're learning math. It creates an engaging environment where students are motivated to demonstrate knowledge through play. Intrinsic motivation drives performance. Sustained engagement occurs over time. An example is SimCity Edu, which assesses systems thinking through city management. It captures process, not just answers, by measuring decision-making strategies, tracking problem-solving approaches, revealing persistence and resilience, and showing how students think, not just what they know. Stealth assessment refers to embedding evaluation seamlessly into game design. Players don't realize they're being assessed. They're just playing. Design principles include assessment intrinsic to gameplay, no separate test mode, continuous data collection, and immediate feedback integrated into game mechanics. Applications include K-12 education assessing curriculum standards through gameplay, corporate training evaluating skill development, healthcare education testing, clinical decision-making, and professional certification demonstrating competency. Studies show game-based assessment reduces test anxiety, increases engagement, provides richer data than traditional tests, and predicts real-world performance. Before we define game mechanics formally, ask yourself, what makes a mechanic truly good? Think of your favorite game mechanic. Is it easy to learn but hard to master? Does it create interesting decisions where different choices lead to different outcomes? Does it feel satisfying to execute with good feedback and responsiveness? Does it have meaningful consequences that affect the game state? These questions get at the heart of what makes mechanics work. A good mechanic isn't just a rule. It's a system that creates engaging gameplay through meaningful choices and clear consequences. Game mechanics are the fundamental building blocks of games, the rules, systems, and interactions that create meaningful gameplay. They include rules defining what players can and cannot do, challenges as obstacles players must overcome, goals defining what players are trying to achieve, actions specifying what players can do, strategies describing how players approach problems, and consequences showing what happens as a result of player actions. A critical distinction exists between mechanics and fluff. Consider the flaming arrow example. Imagine two arrows in a game. A regular arrow deals 10 damage. A flaming arrow deals 10 damage and has a fire visual effect. Are these mechanically different? No. The flame is fluff, aesthetic decoration without mechanical consequence. They're mechanically identical. Now imagine a regular arrow deals 10 damage, while a flaming arrow deals 10 damage and sets enemies on fire for 5 damage over time. Now they're mechanically different. The flame creates meaningful consequences. Why does this matter? Many beginning designers confuse aesthetics with mechanics. They add visual variety without mechanical depth. This creates an illusion of choice with options that don't meaningfully differ, wasted development time creating content that doesn't affect gameplay, and shallow gameplay that looks complex but plays simply. Mechanics create meaningful consequences. A mechanic must change the game state, affecting what happens next. It must create decisions, giving players meaningful choices. It must have consequences, where different choices lead to different outcomes. And it must enable strategies, supporting different approaches to problems. Examples of strong mechanics include jumping in Mario, which changes position, avoids hazards, and reaches platforms. The cover system in Gears of War protects from damage and enables tactical positioning. Card draw in Hearthstone introduces randomness, resource management, and deck building. And the portal gun in Portal solves puzzles, enables movement, and creates spatial reasoning challenges. Focus on mechanics that create meaningful consequences. Don't waste time on visual variations without mechanical differences, complex systems that don't affect core gameplay, or features that look cool but don't create decisions. The MDA Framework, developed by Robin Hunicke, Marc LeBlanc, and Robert Zubeck, provides a formal approach to understanding how games work. This framework is essential for thinking clearly about game design. The 3 layers are mechanics, dynamics, and aesthetics. Mechanics are the rules and systems designers create. This is what the game code does, the formal constraints and the algorithms and data structures. An example is, if player presses jump button while on ground, apply upward velocity. Dynamics are the runtime behavior that emerges from mechanics acting on player inputs. This is what happens during play, the emergent patterns, and the interactions between systems. An example is player uses jump timing to cross gap, barely making it. Aesthetics are the emotional responses players experience. This is what players feel, the subjective experience and the fun of the game. An example is player feels tension, then relief and accomplishment. The bi-directional perspective shows that designers work from mechanics to dynamics to aesthetics. They create rules, hope they produce interesting behavior, and aim to create desired emotions. Players experience aesthetics to dynamics to mechanics. They feel emotions, observe what's happening, and discover the underlying rules. Why does this matter? This explains why game design is hard. Designers create mechanics hoping for specific aesthetics. Players experience aesthetics and infomechanics. There's no direct line from mechanics to aesthetics. Dynamics mediate the relationship. LeBlanc identified 8 kinds of fun as aesthetic goals. Sensation provides sensory pleasure. Fantasy enables make-believe and role-playing. Narrative creates drama and story. Challenge presents obstacle courses and problem-solving. Fellowship enables social interaction and cooperation. Discovery allows exploration and finding new things. Expression enables self-expression and creativity. And submission provides pastime and relaxation. When designing, ask, what aesthetics do I want? What should players feel? What dynamics would create those aesthetics? What needs to happen during play? What mechanics would produce those dynamics? What rules would make that happen? For example, to design tension, the desired aesthetic is tension and suspense. The dynamics needed are close calls, narrow escapes, and uncertain outcomes. The mechanics to create it include limited resources, time pressure, and high stakes. Start with aesthetics. What do you want players to feel? Design mechanics accordingly. What rules would create those feelings? Test the dynamics. Does gameplay produce the intended experience? And iterate. Adjust mechanics based on actual player responses. A common mistake is designing mechanics without considering aesthetics. You create technically interesting systems that don't produce satisfying experiences. Not all mechanics are equally important. Understanding this hierarchy helps you focus design efforts effectively. Core mechanics define the game's identity. Without them, the game fundamentally changes. Characteristics include receiving the most design attention, players interacting with them most frequently, defining what the game is about, and removing them breaks the game. Examples include jumping in Mario, where the entire game is built around jumping, gunplay in Call of Duty, where shooting is the core interaction, card playing in Hearthstone, where playing cards is the fundamental action, and attacking in Smash Bros., where combat is the core mechanic. Primary mechanics directly support the core mechanic, adding depth and variety to the core gameplay loop. Characteristics include being essential to functioning, secondary to core experience, adding complexity and depth, and supporting the core mechanic. Examples include wall sliding and ground pounding in Mario, which enhance jumping, weapon reloading and aiming down sights in Call of Duty, which support gunplay, and minion attacks and hero powers in Hearthstone, which support card playing. Secondary mechanics add variety and depth without being essential. The game functions without them, but they create new experiences and challenges. Characteristics include not being essential to core gameplay, adding variety and replayability, creating new strategies, and being optional or situational. Examples include fire flowers and star power in Mario, which are temporary power-ups, grenades and kill streaks in Call of Duty, which are situational tools, and taunt minions and spell synergies in Hearthstone, which are tactical options. The design principle is to focus ruthlessly. Successful games carefully focus on core mechanics supported by primary and secondary systems. They don't try to do everything. A common mistake is adding too many secondary mechanics before the core mechanic is solid. This creates unfocused gameplay, wasted development time, confused players, and a shallow core experience. When you create a game, identify your one core mechanic. What is the game fundamentally about? Polish it relentlessly. Make it feel great. Add primary mechanics sparingly. Only include what's essential. Consider secondary mechanics only if time permits. They're nice to have, not need to have. The 80-20 rule states that 80% of player engagement comes from 20% of your mechanics, usually the core mechanic. Focus your limited time accordingly. These classic games demonstrate timeless mechanical principles that remain relevant today. Tetris from 1984 features spatial puzzle solving as its core mechanic, rotating and placing falling blocks. Why it works: simple rules create infinite skill ceiling with perfect information. The lesson is elegance through simplicity. One mechanic provides endless depth. Its modern influence appears in match-3 games and spatial puzzles. Super Mario Bros. From 1985 features precise platforming as its core mechanic, jumping with precise physics. Why it works: responsive controls, clear feedback, and escalating challenges. The lesson is that feel matters. Mechanics must be satisfying to execute. Its modern influence appears in every platformer since. Pac-Man from 1980 features risk-reward navigation as its core mechanic. Navigate maze while avoiding or chasing enemies. Why it works: clear goals, dynamic risk-reward, and power fantasy reversal. The lesson is that simple mechanics can create complex strategic decisions. Its modern influence appears in chase-escape mechanics in countless games. Space Invaders from 1978 features pattern recognition as its core mechanic, shoot descending enemies. Why it works: escalating difficulty, pattern learning, and reflexes. The lesson is that difficulty curves maintain engagement. Its modern influence appears in shoot-'em-ups and bullet hell games. Halo from 2001 features regenerating health as its core mechanic. Health regenerates when not taking damage. Why it works: encourages tactical retreat, reduces frustration, and maintains pacing. The lesson is to remove friction that doesn't serve core experience. Its modern influence is that it's now standard in modern shooters. Portal from 2007 features the portal gun as its core mechanic. Create linked portals on surfaces. Why it works: one mechanic with infinite creative applications. The lesson is depth through interaction. Simple mechanic creates complex possibilities. Its modern influence appears in physics-based puzzle games. Minecraft from 2011 features block placement as its core mechanic. Place and remove blocks. Why it works: emergent creativity, clear feedback, and infinite possibilities. The lesson is that simple mechanics enable player expression. Its modern influence appears in sandbox creation games. Dark Souls from 2011 features stamina management as its core mechanic. Actions consume stamina, requiring tactical resource management. Why it works: every action has weight and consequence. The lesson is that constraints create meaningful decisions. Its modern influence created the Souls-like genre. Common threads include simplicity, as core mechanics are simple to understand; depth, as simple mechanics create complex possibilities; feel, as mechanics are satisfying to execute; clarity, as feedback is immediate and clear; and scalability, as mechanics support increasing complexity. You don't need to invent new mechanics. Taking proven mechanics and combining them in new ways, applying them to new contexts, polishing them to perfection, or adding unique twists can create compelling experiences. You're entering the field of game design at an extraordinary time. AI-augmented design provides tools that amplify creativity, enable faster iteration and prototyping, create new possibilities for small teams, and democratize game development. Your advantage is that you're learning game design alongside AI tools. You'll integrate them naturally rather than adapting to them. Game mechanics aren't just for entertainment. Broader applications include education through serious games transforming learning, healthcare through games for therapy and rehabilitation, social change through games addressing real-world problems, and research through games advancing science. Your skills will apply beyond traditional gaming. Technology changes rapidly. Game engines evolve. Platforms come and go. But good game design endures. Timeless principles include meaningful choices, clear feedback, appropriate challenge, satisfying mechanics, and emotional resonance. Master these, and you'll succeed regardless of technological changes. When you create games, remember to apply what you've learned, focus on core mechanics, test early and often, learn from every iteration, and most importantly, have fun. After you create games, reflect on what worked and what didn't, document your learnings, play and analyze other games, keep making games, and build your portfolio. Resources for continued learning include game design books like The Art of Game Design and Rules of Play, GDC talks available free on YouTube, game design communities like the Game Design subreddit and game dev forums, game jams like Ludum Dare and Global Game Jam, and online courses in game design programs. Remember, every great game designer started where you are now. The difference between them and everyone else? They kept making games. Your journey is just beginning. Games are one of humanity's oldest and most powerful forms of expression. From ancient Senet to modern AI-driven experiences, games have entertained, educated, and connected us. Now it's your turn to contribute to this legacy. Make something amazing. Make something meaningful. Make something yours. Good luck with your game development journey. Please visit www.alexpfeiffer.at or www.mtech-lab.at if you'd like to learn more about emerging technologies in gaming.